You know, for decades, scientists have been trying to build quantum computers out of pure light. It's a beautiful dream. But there's always been this one really stubborn problem that stood in the way, a flaw that made the whole thing seem, well, kind of impossible. So today, we're going to look at the incredibly clever workaround that is completely changing the game.
Right, so let's get into it. Photons, particles of light, are almost the perfect thing for carrying quantum information around. They're super fast, they're really robust against noise, but they have this one killer flaw, one critical weakness that's been a massive roadblock for years.
So what's the deal? What makes light so good for this job? And what's the one thing that's been holding it back? Let's break it down.
The perks of using photons are just huge. They move at the speed of light, obviously. They're incredibly resistant to noise from the environment, which is a major headache for other types of quantum computers, and you don't need these giant, super expensive refrigerators to keep them stable. But here's the big catch. Photons are lone wolves. They just don't like to talk to each other. And for a computer to, compute, its qubits have got to interact. So solving this interaction problem, that has been the central challenge for a long, long time.
All right, so scientists had this problem. How'd they try and fix it? Well, for a long time, the whole field basically split into two completely different camps, two competing philosophies on how to get these photons to play nice.
So on one side, you had the discrete-variable, or DV, approach. This is beautifully simple. Think of it like Morse code. A single photon in this path is a 0, a photon in that path is a 1. Super clean, super clear. The problem? Getting two of these qubits to interact is literally a coin flip. The gates you need to entangle them fail 50% of the time. You just can't build a reliable computer like that. So, on the other side, you have the exact opposite idea, bosonic encoding. Instead of simple single photons, you use these really complex, powerful states of light called cat states. This is like a full symphony instead of Morse code. And with this power, you can do operations that work almost every single time. The catch? These symphonies are super, super fragile. If you lose even one photon, the whole thing can just fall apart.
Okay, so when we say symphonies of light, what are we even talking about? This gives you a bit of a visual. Up top is your basic cat state. In the middle, you've got this more robust, four-headed version. And down at the bottom is the GKP code, which is one of the most powerful and most complicated ways to encode this stuff. They look cool, right? But yeah, there's a huge catch. And that catch is, well, this quote kind of says it all. Making these things in a lab is just brutally difficult. So you see the problem, right? Scientists were stuck between a rock and a hard place. You had a simple method that was too unreliable and a powerful method that was too fragile to actually build. It really seemed like a dead end.
But then, out of this whole mess, a really clever new idea popped up. A new strategy that didn't pick a side, but instead just took the best parts of both.
What if you didn't have to pick? What if you could take the simple reliability of the single photon and combine it with the raw power of the cat state?
And that right there is the big idea behind the hybrid qubit. It's a brand new kind of quantum bit. It's not one or the other. It's literally both, glued together at a quantum level. You have a simple single photon part entangled with a complex cat state part. It fuses the two opposing philosophies into one.
Now, this diagram might look a little intimidating, but the idea behind it is actually genius. When you want to do a key operation, you don't measure the whole thing at once. Instead, you do a simple, reliable measurement on the single photon part, that's the red bit, and you do a separate, powerful measurement on the cat state part, in blue. By combining the results, it's like they're covering for each other's weaknesses, and the end result is an operation that's incredibly reliable, with a failure rate that gets smaller and smaller as you make that cat state more powerful.
So what this really gets you is the absolute best of both worlds. The single photon part gives you that clean, unambiguous result, just like the simple DV approach. But the cat state part gives you that near-perfect success rate you get from the bosonic approach. And together, they allow for something called ballistic operation. It means the computer can just go. It can run its calculations without needing to stop and check for errors every 5 seconds, which makes the whole thing so much simpler and faster.
Okay, so this sounds great on paper, right? But is anyone actually building this? You bet they are. Let's take a look at what's happening in the lab right now. This table really shows you how fast things are moving. Just focus on that last column, loss threshold. That's basically a measure of how much can go wrong, how many photons you can lose before the whole thing falls apart. And look at that jump. In just a few years, researchers have pushed that number from a tiny fraction of a percent to over 1%. That is a huge deal in terms of making this stuff practical.
And this is what it looks like when you get your hands dirty. Don't worry about tracing every single line here. The point is, this isn't science fiction. Scientists are already in the lab using real hardware, real lasers, real beam splitters, and they are making these special hybrid states right now. The fundamental building blocks exist.
So okay, you can make one. How do you build a whole computer? Well, this is the blueprint. The idea is you start with small clusters of these hybrid qubits. Then you use those super reliable hybrid measurements to fuse them together, basically stitching them into this massive error-tolerant 3D structure. This is the roadmap to a large-scale photonic quantum computer.
So how close are we, really? Well, this number, alpha, tells a big part of the story. You can think of it as the power level of the cat-state part of the qubit. The bigger it is, the better. Now, the theories say you need an alpha of at least 0.84 for this to work well. And the fact that experiments have already hit 0.9, that is a huge milestone. It means we're basically knocking on the door of having the hardware quality we need.
But here's the really cool part. This isn't just about building one kind of computer. This whole hybrid idea is a fundamental new tool in the quantum toolbox, and it has implications that go way beyond just one machine.
So let's just recap the big wins here. 1, it's way more efficient. You get more bang for your buck with fewer qubits. 2, the operations almost never fail, which cuts down on errors. And 3, it runs ballistically, which makes the whole architecture simpler and faster. It really does solve the core problems that held this field back for years.
And because this tech is so robust and so efficient, it's also the perfect candidate for building a quantum internet. We're talking about quantum repeaters that can send quantum information over long distances. This could be the very backbone of a future global quantum network.
And get this, it can also act like a universal translator for the quantum world. Scientists have shown you can take quantum information from a simple single-photon qubit and teleport it into a complex cat-state qubit and then back again. This ability to switch between different quantum languages is absolutely critical if you want to build a network that can connect all sorts of different quantum gadgets together in the future.
You know, when you step back, the story of the hybrid qubit is just a powerful reminder that sometimes the best answer isn't about choosing one path over another. It's about finding a clever way to combine them. And it really makes you wonder, what other impossible problems out there are just waiting for the right hybrid hero to come along and solve them?